All right, folks, let's get ready to re-engage here. All right, very well done on your quiz scores there. Want to make certain you guys repeat those quizzes now multiple times. Okay, do them again and again and again. That is one of the most important ways that you can prep yourself to pass this certification exam. And don't forget, as I told you guys, all of those files that I gave you guys for download on the wormhole site, make sure you grab those. You don't want that link to expire on you. And those are some good study documents on that link as well. All right, let's dive right on in here to module number 6. Here we start talking about the methods that we utilize in order to set up your addressing, set up the proper addressing functionality on your as far as your IP addressing goes there, to allow you to connect to the World Wide Web and to communicate out over that network. Okay. Now, I spoke to you earlier about the Internet Exchange Points, the IXPs, and the fact that all of your internet service providers, whomever your service provider might happen to be, they have all of their routing and switching and data equipment set up typically inside these massive data centers where all of the infrastructure for the internet worldwide terminates into these massive internet exchange points. I got the opportunity to visit one. The only thing I can tell you is it's somewhere on the East Coast. I'm bound by a non-disclosure agreement not to reveal the location, but I can reveal to you it is awesome. It is the largest data center collection and the largest number of terminating wires that I've ever seen in a single location. I mean, just unbelievably massive size data center. And of course, all of the local internet service providers have all of their cages and their routing and switching equipment set up in there as well. This is what I was talking to you guys earlier about in your small office, home office type of environment. The router device here set up, that's typically the router, the switch, the gateway, and it also performs the functionality of what's called a modem. A modem is a modulator demodulator. It actually takes in digital data, converts it to, if it's required to be presented in an analog environment, and vice versa. It does analog to digital conversion there as well, and sends it out over the digital network. Now, in our current IP addressing scheme, we are using a 32-bit binary address. When the Internet Engineering Task Force first came to be and started defining the framework and the requirements for IP addresses, most of the computer systems at that time were 32-bit processors, 32-bit data paths. So they defined this 32-bit IP address. And now we see it, we don't look at it as binary. We human critters look at our IP address in the numeric fashion, similar to this right here. You know, very common. This is called a class 3 private computer IP address, 192.168.0.1 or 192.168.5.128. Those are all versions of private IP addresses. Now, the router device, the gateway router access point device, actually plays another couple of functional roles as well. It performs a function called network address translation, NAT. It's called a NAT server. It keeps private IP addresses private, and they're only housed inside of a private computer network. If you're going to be communicating out over the public internet, then that router gateway device there, the NAT server, takes your private IP address and other bits of information, date and time stamps, communication ports you're communicating on, and then it creates an instance of your company or your service provider's public IP address. And then that is transmitted out over the public internet. Your router gateway device tracks that session, tracks the communication ports that it went out on. And when the reply comes back from that, it translates that back to your private IP address, which then gets translated to the physical MAC address on your computer system, and the message is then delivered back to you. So it's a couple of different translation steps along the way in order to maintain your private IP address as private and only expose the public IP addresses. Now, what the Internet Engineering Task Force did, and a couple of other organizations, they came up with this 32-bit addressing scheme, and that will actually accommodate somewhere in the neighborhood of about 340 billion addresses, okay, total, and that's the addresses that fit in that 32-bit scheme. They sort of carved that almost in half, and they says, all right, we're going to dedicate these ranges of IP addresses to private IP addresses. Those will be contained inside of autonomous networks, not shared out over the public internet. And then the remaining addresses, there's a couple of them that are very specific for particular functions. I'll touch on some of those later. But then the other addresses are housed by two different organizations, and they call it leasing those addresses to companies, private companies, institutions, banks, academia, whatever. Most companies only have one, sometimes two public IP addresses that are leased to them. Those are relatively small companies. And there's an organization known as ICANN, I guess it's the Internet Committee for Assigned Names and Numbers, or the Internet Corporation for Assigned Names and Numbers. So they lease those public IP addresses to companies. And like I say, most companies only have one. So all of the traffic coming out of their perimeter router looks as if it's coming from the same IP address. And then the NAT server inside their router actually translates it back to delivery to the individual users inside their network. Some companies, larger companies, may get two, three, a group of public IP addresses leased to them. And then some companies, like for instance, internet service providers, they have these large blocks of public IP addresses leased to them. There's actually three different classes of private IP networks. I'll tell you about the ranges of IP addresses that belong to those in just a little while as well. The very first couple of digital connectivity to the internet was accomplished by these modems called DSL modems, digital subscriber line modems. That was when the majority of people were connecting to the internet based upon the standard, the old telco guys used to call it POTS lines, plain old telephone service, the public switch telephone network. That was the lines that ran into everybody's homes and delivered regular analog telephone service. So these DSL modems, that analog line would plug into the DSL modem, and that modem would translate that analog communication coming in off of the public service telephone network into digital data. And then there was typically an Ethernet cable that either connected to an external modem, or the modem functionality was built into this box. And then that Ethernet cable then was hooked up to either a hub or directly into a computer system. Okay? So that's what gave us that 8-wire twisted pair connectivity with this DSL modem. These things were relatively slow speed it was screaming speed for the time, but they were, the upload speed and the download speed were different. The download speed was somewhere, they say that they would give you up to 25 megabits per second. I never used one that got more than 8, 10, maybe 12 megabits per second download speed. And the upload speed was just ridiculously low, 3 to 6 megabits per second, relatively slow. Then we started seeing the modem functionality, the router functionality, the digital subscriber line functionality scaled down out of these big boxes here into little tiny boxes like so. So again, the telephone line would come into one of these telephone ports. You'd have another telephone port out of this guy that hooked up to your telephone system, your analog telephone system. And then this switch here, the RJ45 plug, would then go into your router, your modem box. And there was actually three different flavors of DSL modem. There was one called ADSL, asymmetric digital subscriber line. Download speed, like I say, about 30 megabits per second, but you never got that. And upload speed, 6, 8, maybe 10 megabits per second. Then they had an upgraded version of it called symmetric digital subscriber line. It was the same speed, upload and download, but you had to be closer to the telephone company, closer to what they call the POP, the point of presence. And I mean physically closer. And then they had a version of it called VDSL, very high speed digital subscriber line. You had to be right next door, basically, to the telco, to the provider to get that high speed. But and it was decent, you know. They actually, when they started installing it, they were touting that, yeah, we'll give you 100 megabits per second upload and download. You never got it, never got it. But they would tell you that they would give that to you. Then we started seeing cable, the coax cable, same kind of coax cable we used to use for our, satellite TV kind of thing. The coax cable modem also was the router gateway modem device all baked into one. And for the longest time, that's how most people were getting their home entertainment, their TV channels, all of that, and their internet connectivity in that cable modem. It utilized an operating system, and many of them still do in different parts of the country, called DOCSIS. And it was that is, operating cable system interface kind of thing there. The cable there, most of them, you had the F-type connector, the screw-in connector from the coax cable that plugged right into this modem here. And then you had an Ethernet cable that came out of that, either to a switch device or again straight into the computer network interface card as well. Then we started seeing fiber. For the longest time, they were in large neighborhoods here in the greater Atlanta area anyway, small, medium, and large networks or neighborhoods. They would run what was called fiber to the curb. The fiber optic cable was laid in the ground, and it would come to these little substation things that you'd see them at the end of streets and cul-de-sacs, things like that. We had one here in our cul-de-sac. It was fiber to that device, and then they had the signal translator, and the cable, coax cable, ran into our homes. And there was one company that came in here, and it was just a short period of time that it was fiber to that collector node, but they were offering RJ45, 8-wire twisted pair connectivity from that node into our home. Didn't work really well. Lawn people come in, cut right through it because they didn't bury it deep enough. Then finally here, about a little over a year ago now, in this location and my alternate location at our cabin, we finally got fiber to the premises, they call it, fiber to the home. And the new fiber optic cabling they're using now as well just blows me away. When I had about a 30-degree bend radius, if you bent it any more than that, you would crack the cable and destroy the cable. You'd have to put new ends on it and rerun cable in some cases. Now, boy, the cable they ran here in the other location, they trenched it in the ground, came up by the wall, and almost did a 90-degree turn going right through the wall into the modem there. Blew me away. And the engineer was telling me about they're using some pretty sophisticated composite materials now. They're not using the solid glass cores anymore. It's a composite. It's glass, plastic. Even somebody mentioned the term transparent aluminum, which I'd never even heard of that before. But this is some of the wireless connectivity. Say WISP networks, WISP, wireless internet service providers. Those are the ones I was talking about that use the large antenna, the dipole antenna for transmitting the signal. And now these guys, the LEO satellite grid, that's Elon Musk. What is it? SpaceNet or SpaceNet, Skynet? Not Skynet. SpaceNet, I think is the name of it. But it's very low Earth orbit, they're only about 550, 600 miles up, whereas the older TV satellite networks, 22,000 miles up. So, and these are grid-based low Earth orbit grids as well. So when you position your antenna, you're actually receiving signals from multiple satellites simultaneously. So it's much better service, much greater speed, much less latency as far as broadcasting the signal. And again, the price on those things, especially for the equipment, is beginning to come down pretty radically from what it originally was. So I think we're going to start seeing a lot more of that satellite connectivity. We are also seeing now in the cellular world, especially with the fifth generation, the 5G fifth generation networks, and even the 4G LTE long term evolution is that acronym. Pretty high speed. Lots of people are getting their 5G hotspots, and that's their only internet connection. And it's really, really good, really fast, really good, wireless completely. And it operates over many of the same cellular frequencies that our mobile phones do as well. So start to see a lot of that. Now, in the not too distant past, when they first started introducing the 4G LTE phones, the long term evolution phones, prior to that, there were two basic types of cellular frequencies that were being used. They had what's called the code division multiplexing and the world phones, GSM, global systems there. The CDMA, it required or did not require a SIM card in the phone device, even though many of them had it, but the data was transmitted through the network itself about the subscriber and the phone handset as you move through the network. The GSM, the world phones, were the ones that has always required the SIM card inside the device. Now, since 4G LTE, all of them are GSM phones. Now, some of the older frequencies have been sort of repurposed. We've seen some of the older third generation and base four generation, not the LTE, but the base four generation of cellular has been repurposed now, seeing it used in like agricultural environments and logistics control environments, warehousing environments, that kind of thing. Not so much for long distance cellular communication, but in these enclosed networks. Okay. With the fifth generation cellular network, their modems and their equipment now is using that same multi-input, multi-output. It's mobile MIMO, they call it. So you can bond channels together, increase speed, And with the fifth generation cellular, it is screaming fast. So quite the changeover now. A lot of people are gravitating towards that wireless connectivity. The router in your home network is in my opinion, an absolutely brilliant device. The routers moves traffic based upon the IP address that's assigned to each individual workstation, whereas the switches largely moves traffic port to port based on the physical MAC address. Now, the IP address is a dynamically assigned address. Very seldom now are many network engineers manually assigning IP addresses. The IP addresses also, it gives me the ability, for instance, within a certain network segment, there's what's called a broadcast address. So if I want to send the same message to everybody in the network, I don't have to send multiple messages. I just send one message to that broadcast address and everybody gets it. Okay. There is basically the three classes of private address groups, and I'll show you what those address ranges are within that 32-bit binary here in just a moment. But the routers allows me to basically subdivide individual either components of a network or networks as a whole. Okay. We also have the networking equipment here called firewall. And as I told you guys earlier, there's lots of aggregation of these different network appliances here. The firewall, the router, the switch, the gateway, even sometimes the antivirus, anti-malware package is included. in these aggregated large server class machines that are playing all of these roles here. The firewalls are basically a filtering kind of system, and they operate much like some of the other network equipment. We'll talk about some of the other equipment later as well. They operate on what's referred to as access control entries, ACEs, and each of those is a filter or a rule, and you set up what's called an access control list. Data frame packet gets introduced into the firewall, it just goes down the list, and is set up in what's called a whitelisting or an implicit deny mode. Anything that is not implicitly allowed or explicitly allowed is implicitly denied. So it goes down the rules: allow this, or allow this, or allow this, or allow this, but deny everything else. Called whitelisting or implicit deny. I can look into the header of each and every data frame or data packet and make decisions about the filtering there based upon the source or the target IP address, the MAC address that's included, the specific communication port or protocol, software protocol that's being utilized to communicate. And then some other things I can look a little bit deeper into header information there and decide I am either going to allow this data frame to flow on through, or I'm going to block it. I'm just going to drop it off the network. They call it tar pitting it or black holing it. So I make those decisions in the firewall. Now, there's a whole crowd of firewalls. Most of them now are software based. Back in the early days, we used to have these big honking hardware based firewall engines that had their own unique programming languages that we had to do some pretty sophisticated programming. Here's one from a company called OpenSense. That is a firewall, and you go in, basically set up the rules, and the rules are processed top to bottom. You decide, what you're going to be filtering. Is it filtering on a certain port number? Is it a protocol? Is it an IP address? Is it a MAC address? Is it software? You decide what the filters are going to look like in that firewall device there. And those are just some of the functions now that we are seeing that are performed by these multifunction network devices here. The router, the switch, the firewall, the gateway, the antivirus, anti-malware kit, all of those things. Okay. Now, these networks, the network structure that we have here on the World Wide Web, the internet, is referred to as TCP/IP.
Sir,
I'm sorry, go ahead. Yeah.
before you get to TCP, for a question about the firewall, if you wanted to download a firewall for or put in a firewall for every single computer on
Right.
the same network,
Mm-hmm.
um, are you saying do we have to have a specific physical device for that, or is it more like a software that you download for every?
Yeah, it's the most of them are software based now. As a matter of fact, in the Microsoft operating system, if you have a professional license or above, there's a very sophisticated firewall built into the Microsoft security kit. It's called Microsoft Defender is the product, and it includes the Microsoft firewall software piece as well as your antivirus, anti-malware kit in the Microsoft Defender. You just need to go in and configure it. The majority of them now, Kaylee, are software based. You
Okay.
don't have to have a particular piece of hardware anymore to run these things. And I'm seeing now as well, lots of the router gateway appliances also include configurable firewall software as well. Okay. So thank you, ma'am, for the question. Good question there. Now, in the IP internet world, this concept here is called Transmission Control Protocol Internet Protocol, TCP/IP. And it is a whole suite of software communication port combinations and a suite of communication oriented protocols in general. In the not too distant past, we used to teach, especially in our networking arena, we're still doing some of the networking classes. We used to teach a 7-layer network model. Now the industry has begun to move more and more towards this model here, which is a 4-layer model. And it's a means graphically and standards wise for me to associate different pieces of hardware, different pieces of software configurations, and different concepts as far as communication goes to one or the other of these four layers. The and all communications begins with some kind of application program. That's the application layer. And it actually is numbered 1, 2, 3, and 4 from the bottom up. But all communication sessions begin with an application. Once you determine what the application program is going to be, say if you're visiting a web page, well, that would be either the HTTP or the HTTPS protocol. So I fire up my web browser and that starts that application. And then that frame then is sort of passed down to the next layer, the transport layer, and it makes the determination of things such as, based on the protocol that I'm using, the software protocol, in this case, HTTP, Hypertext Transport Protocol, it says, okay, well, the default communication port on the system I'm going to be talking to is, if it's HTTP, it's port 80. And if it's HTTPS, it's port 443. So the transport layer says, all right, that is this type of communication session you're wanting to do. So I'm going to be targeting those ports on the target system. And it is going to be one or the other of a different type of transport communication mode. Now, I'll talk about these in more detail later, but basically, there's two different modes of communication. There's the transmission control protocol, which is interactive. Okay, it is timed, it's sequenced. The session itself is established and acknowledged and all that good stuff. It guarantees not only the integrity of the data as it's sent and received, but it also guarantees the delivery of the data. Okay. On the other hand, the other protocol is called UDP, User Datagram Protocol. It's just what they call best effort. It starts blowing data down the pipe and hopes you receive it. If a frame is dropped, oh, well, I don't resend it. You don't ask for it again, that kind of thing. So once it wraps that up and determines the communication port or ports you're going to be using based on the type of application protocol that's being run, then it passes on down to the internet layer. That's where you get your IP address. And that typically, gives me information that I then pass on down and says, well, am I communicating locally or externally? So it passes on down to the link layer, the network interface layer. And I want you to notice, sort of hovering in between these two, this little guy here that says ARP. That is Address Resolution Protocol, ARP, Address Resolution Protocol. Its responsibility is to make the connection between the IP address that your session receives and the MAC address, which is your physical address on your NIC. So it joins those two together for the duration of your session. Okay. So the IP address, remember, is used to communicate logically out over the network. And the MAC address, the physical address, is used to communicate typically inside your network, port to port, in the switch type of environment. Okay. Kathleen, I want to welcome you to the party here. I want to take a brief moment to welcome you in. And I also highly encourage all of my students, get you logged into my roster here so we can keep track of you. I encourage you and invite you to ask questions. As I'm going through the lecture here, if you come up with a question that you want to ask, you feel free to dive in and do it. You can raise your hand on your workstation there. You can turn your mic on. You can type it into the chat box, either way. And when you do that, I will try my best to answer the question. I don't consider it an interruption. I consider it an opportunity. So you feel free to participate as much as you wish. Okay? So then when you make that connection between your IP address and your physical MAC address, that information updates this area called your ARP cache. So that cache then follows your session for the whole time you're logged in and tracks. Anybody communicates with your IP address, the ARP cache says, oh, okay, that's this MAC address, and routes it or switches it over to your particular system. Okay. So a lot of things are performed down here at the link network interface layer. That's where it, that if it's a MAC address thing, well, your switch will be associated with that layer. If it's an IP thing, then your router will be associated with the internet layer there. Okay. Down here also in the link layer, that's where your network interface card is located there as well. So that will assist me later on in even doing troubleshooting functions. If I'm trying to track back the network layer, if I figure out what the hardware is, that also may alert me to some of the software issues that I may be having at one of those layers as well. Okay. The network frames, individual data frames and packets, are referred to as PDUs, packet data units there. It exists with a header and then the data payload and then a trailer on each one of those. Remember, the MAC address is used for going port to port communication with your from switch to switch port. That MAC address is included in that PDU. Once it goes through the ARP cache, then that's translated into your IP address for forwarding outside of your network or outside of your network segment. Okay. So the PDU is updated there. And then the transport layer is what updates that PDU with the protocol, the port number you're communicating on based on the protocol you're using and so on. Updates the PDU with that. And then the application layer is, like FTP or HTTP or Telnet or, whatever the protocols, software protocols may happen to be there. So all of that information then is updated inside of the data unit, the packet data unit there as well. Now, here is some pretty clever stuff, and I think you're going to have fun with this. I always do. I'm going to show you toot sweet here how we translate a binary address into its numeric equivalent. First, I want you to realize the binary is a base 2 numeric system. Okay. There are only 2 digits in a binary numeric system. There's ones and there's zeros. So the 32-bit binary address, the Internet Engineering Task Force they work with the ICANN organization I was telling you about, the EIA and the TIA. And they came up with this scheme of taking that 32-bit binary address and breaking it down into 4 sections that we call octets. Okay. And those are 8 bits per octet. Now, that was clever and interesting because all your characters on your keyboard, the computer stores and recognizes those as 8 binary bits, combinations of the ones and zeros. So each of these octets, in order to translate the binary data into its numeric equivalent, we use what's referred to as powers of 2 placeholders. These guys right here. I want you to remember something. These are constant. They never change. All numeric systems begin with a 1. Now, some mathematicians and those that claim to be mathematicians will tell you that no, numeric systems begin with 0. Well, 0 is not a real number. It is nothing. There's nothing there. So we begin with 1, and everything going left here is powers of 2, and it's a total of 8 placeholders. So 1, 2 to the first power, 2 to the second power, third power, and so on. Remember, these are constants based on the binary numeric system. They never change. So if I take these 8 binary bits here, down here, and I associate those with each of these placeholders, okay, in order for me to derive the numeric value of those 8 binary bits, everywhere in those placeholders, I have a 1. I add the value of that placeholder. So in this case, I add 128 plus 64 equals 192. So that is the first octet address here in that 32-bit binary address. If I do the same thing with the second octet of binary data, okay, it totals up to a value of 168. Okay, 1 plus 0 plus 1 plus 0 plus 1, okay, 168. So the first two portions of my IP address there are 192.168. Okay, and then just do the math here on these last ones. The all zeros there, well, that's 0. Over here, the only binary bit that is true or turned on is the placeholder for the value of 1. Okay, now I want you guys to kick in and do this for me. I am wanting to give you a binary value here. You tell me, based upon what I just told you, what is the numeric value, the decimal value of this 8-digit binary address? 11010001. And when you calculate it up, just type it in your chat box or turn your mic on and shout it out. Either way will do. So pull the old trusty calculator up and do it. So I'm going to add the value of 128 plus 64 plus 16 plus 1. And Alex says 209. Do you concur, Kaylee? And Kathleen, do you come up with that same value there? You should, because that is correct. Absolutely. Yeah. So that is how you do it. So if I take that binary digit here, okay, take this and same thing, associate it over here, okay, whatever the placeholder values are there. Everywhere there is a 1, I add the associated placeholder value. And that's how I calculate the numeric or the decimal equivalence of binary data. Okay. So that's the deal there, right? 128 plus 64 plus 16 plus 1. Now, one of the files that I gave you guys to download off of that wormhole site was a binary to decimal to hexadecimal spreadsheet. So you can play around with that at will, and you'll see what I'm talking about. Now, inside of each octet, there could be a possible total value of 255. Okay. Now, here's what I do as far as subnetting. In order for me to, or for my gateway device to determine if I'm wanting to do an internal communication or an external communication, it uses what's called a subnet mask. There are 3 forms of private network classes: class 1, class 2, and class A, class B, class C, or class 1, class 2, class 3. Okay. Either way you look at it there, it breaks your network down into the full decimal IP address, which of the octets are the network address portion, and which of the octets are left for you to calculate host addresses. Okay. So there are 3 different class sizes on your network, and here's what those are: class A, B, and C. Now, here is what your addresses, the network addresses or the subnet mask look like when we pull these guys up here. For the class A type networks, those are super large networks, by the way, class A networks. That's the ones that you'll see that, for instance, your ISP is typically a class A type of network, very large networks. And the total number of addresses there could be almost 17 million host addresses within those networks. That subnet mask looks like this. Oh, I'm sorry. That is the class A subnet mask right there. And what that says is, of this total IP address range here, the first 3 octets or the first octet is the network address only. And that can be a network address anywhere in the range of 1 through 10. Okay. And then the number of available addresses that I can assign, I'm sorry, 10 through 10 dot, 10 through 10, the network address. The last 3 octets I can use to calculate host addresses within the network addresses over here. Okay. And that is actually 255, it says, but they use 0. So 0 through 255 is 256 addresses available. So I do 256 times 256 times 256. That is almost 17 million available host addresses. Now, the class B networks are, it masks out the first 2 octets within this range, 172.16 to 172.31. Any network addresses fall in those first 2 octets, leaving the last 2 octets, or 255 times 255, that I can calculate host addresses within the network address. Okay. And that's 65,534 is that calculation, by the way. The Class C networks, which is the largest number of private networks, fall into this category. It masks out the first 3 octets as the network portion of the address, leaving only a total of 256 available addresses that I can use as host addresses. Now, there's a caveat there. We discount address 0 in that range, and that oftentimes is utilized as part of the network address. So we really only deal with addresses 1 through the top end. 255 in this case would be what we call the broadcast address. I mentioned that earlier. If I have a network or a private network here, a Class C type network, and I want to, let's say my network address is 192.168.5, and I want to broadcast the same message to every workstation in that network, I will broadcast that message to address 255. I don't have to send the same message to everybody in the network individually. That broadcast address, which is the high order address in that range, will allow me to send the same message to everybody in the network. Okay. So it leaves me then a total of 1 through 254 that I can assign as host addresses within this network address. Okay. And the reason that those first 3 octets of the network address is because of this subnet mask. Okay. And I told you earlier, the network address translator, which is typically part of the router gateway device, it does the translation between these internal private IP addresses and whatever public IP address I have assigned to my company for outbound communications over the World Wide Web. Okay. Now, here is an example also, and I'll show you, of how that subnet mask actually works. Okay. Let's say my IP address is 192.168.5.15. I want to communicate with a workstation whose IP address is 192.168.5.125. Okay. Now, that is within the range, you'll notice, of the Class C private IP address scheme, these guys here. Okay. So I know my subnet mask is 255.255.255.0, which says that the first 3 octets of this IP address is the network portion of the address. Okay. So I lay that subnet mask over each, the source IP address and the target IP address. And because I'm masking out those first 3 octets, I ask the question, am I in the same network? Yes, I am. So more than likely, the router will just bump that message back to whatever switch it came from and says, look, this is in the same network. You communicate using the MAC address, port to port. Okay. Now, let's say that I was wanting to send a message to this IP address. Same thing, it's still a Class C network. So I overlay the subnet mask and mask out these first 3 as my network address, mask out these first 3 as the network address. They are not the same. So now the router looks into its routing tables and figures out where it needs to forward that message to either a different subnet inside my same network, or if I am communicating with something like this, the router says, okay, that's a completely different network altogether. So I'm sending that out there. Well, it would be something like this, not 168, but 172.16.7.125. Completely different network. I route that out over the public internet. And the NAT server would take that address, mask it in the message, and when it was received by the other private network, it would go through that translation and end up being delivered to the MAC address that belonged to this IP address in that completely different network. So the NAT server is what does that public to private, private to public translation there. And it's designed to keep the private IP addresses private. You must memorize these ranges right here. Okay. Make you some flashcards. Associate those with all of those subnet masks. Class A subnet mask 255.0.0.0. Class B subnet mask 255.255.0.0. Class C subnet mask, and this is the largest number of networks you'll find worldwide, 255.255.255.0. Okay. So that is your addressing. There's the information. Now you are beginning to see this notation here on IP addresses. Okay. This is called CIDR, CIDR, and that is classless interdomain routing. It sort of throws away this old subnet mask concept, and it allows us to, in my opinion, to more efficiently utilize IP addresses. We are literally running out of publicly available or private IP addresses on the World Wide Web because so many people have so many devices. This /8 CIDR notation is exactly the same thing as this subnet mask. It says the first 8 binary bits of the IP address is the network portion of that address, leaving the last 3 octets or 24 bits that I can use to calculate host addresses. Down here, /16, same thing as the Class B subnet mask, 255.255.0.0. The first 2 octets of the IP address is the network portion, leaving the last 2 for calculating host addresses. /24, same thing as the Class C network. Okay. So in order to answer the questions on your exam, remember these ranges here. Remember the subnet masks that go along with those. Remember that this is the same as this subnet mask. This is the same as this subnet mask. And this is the same as this subnet mask. And over here's what it looks like in the binary mode. Okay. So that's what you have to be aware of. Now, when network engineers are setting up the addressability in a network environment, they can decide either to do it statically, manually, as it were, or they can decide to do it smartly, more intelligent method, and use a protocol called DHCP, Dynamic Host Configuration Protocol. I'll talk about that later. If you're going to be manually configuring each individual computer system, you'll have to go to those individual computers and you'll have to do their internet connectivity. When you're doing that, you provide a couple of different bits of information. You choose whatever IP address you're going to assign to that device. You type it in. You choose either the subnet prefix, and some of the older versions of the operating system, you have to actually key in the full subnet mask. Then you select the IP address of both your gateway device, which is typically the router that is closest to you, okay? Or and I'm sorry, not or, but and the DNS server. That's domain name services. We'll get to that. We'll get to that later on as well. I'll further define that. You'll notice here that the gateway device, the router IP, and the DNS server are the same. I was telling you earlier that we're seeing lots of aggregation of those multiple functions, especially into that router gateway appliance. You'll also see that you don't have to put it, but an alternate DNS. This just happens to be the Google DNS servers, which are out deployed out all over the World Wide Web. Okay. So if you turn this switch on here, it requires that you manually key in all this stuff. Now, if you want to see somebody make a mess of that, let old dyslexic Donnie turn me loose on having to go around to each individual host computer and having to manually key that stuff in. Okay. Yeah, it's I can make a mess of it big time. Now, I was talking about the leftover IP addresses that don't fall into one of those class A, B, or C realms. There's one very specific set of IP addresses. And if I were a betting man, which I used to be, I would bet $1 to a donut that you will have a question about this range of IP addresses. It's called a PIPA, automatic private IP addressing. Here's why it happens. First, always remember, a PIPA addresses always begin with 169.254. Always. Automatic private IP addressing. When I go to log into an IP network, if it is set up in dynamic mode, there's a DHCP server, a dynamic host configuration protocol server, somewhere in that network. My system seeks it out. It locates that closest DHCP server. And the DHCP server says, oh, you're wanting a new IP address. My system offers up my MAC address and says, this is my physical address. I need a logical IP address to go along with it for this session. The DHCP server typically has a pool of available IP addresses that it manages. It takes the next one off the stack and says, here's your IP address I'm offering to you for the duration of this session. Now, my system can decide, well, I don't want that one. I like another one. But 99% of the time, they say, yep, I'll take that IP address. Now, if for some reason, and it could be a whole host of reasons, my computer system cannot contact that DHCP server. The server may be down, the switch may be broken, the network link may be unavailable, whatever. So my system says, well, I need to get online here. So the Windows operating system automatically assigns this a PIPA address, automatic private IP. And they always begin with 169.254. So if you're supporting a network, somebody calls you up and they say, I can communicate with all the users that are in my same department or hooked up to the same switch, but I can't talk to HR and I can't communicate out over the public internet. Well, there's a command that I can use or have them use. It's called ipconfig, and we'll go over these commands in more detail later. That ipconfig command will show me what my IP address is. If they run that ipconfig, or if you're on site and you run it, and their IP address is 169.254.1.35, you know that is a PIPA address. And the only reason you get that is because they could not make contact with the DHCP server and get their session level IP address. That's always the reason. So that will show you where you can start troubleshooting that particular issue. Okay. So remember that you will get a question about it on your exam. Okay. Now, in many cases, also in the router gateway device, that's where you configure the DHCP server. You go in through its management console and you set it up and you say, all right, well, you are going to be servicing this section of computer systems over here. You're in their same network segment. And here is the pool of addresses that you have available to assign to these systems when they come online. So you go and you set it up. You give it the range of IP addresses. You key in what their subnet mask is right here. You key in what their network gateway device is, what their router gateway appliance is. The DNS server, you key in that information as well. You key in what their gateway device is, which oftentimes may be the same device here. So you configure and set up all of that. Okay. Now, in your small office, home office kind of environment, you may have different network connections. You may even have multiple NIC inside of a singular computer system that has links to multiple networks. Each and every one of those networks will have to be configured and to, in essence, know your computer system. And your computer system will have to have multiple interface connections so that it can indeed connect to all those different networks. When you start setting up your router, the router, as I was telling you guys earlier, is an extremely intelligent device. It makes real-time dynamic decisions on what the most efficient route from one location to another location inside of a network happens to be. So through the management console, you go in and set up all the functionality of that router. You set up things such as again, what the gateway appliance is, what the IP address, and it's usually the same device, the router itself. Now, in the IP version 4 world, that's what we just looked at with the 32-bit binary address. The new version, or the next flavor, if you will, of the internet is going to be using what's called IP version 6. It is a 128-bit binary address. And we won't be seeing that address anymore as a decimal value. It will be showing up as a hexadecimal address. Looks very similar to that same example I gave you of the MAC address, only longer. Okay. In the IP version 6 world, that whole address space will accommodate it's a numeric term I'd never even heard of before. It's called 300 undecillion, or 300 trillion available addresses in that 128-bit scheme. Okay. That is way, way more addresses, unique addresses, than this and a couple of other planets will ever use. Currently, with the population of our world, that would accommodate every user on the planet. There's a little over 6 billion of us on the planet right now. Well, every user on the planet to live in that address space could have thousands of individual devices, mobile phones, tablets, phablets, desktops, laptops, security systems, smart glasses, whatever, anything that requires an IP address Each individual person on the planet could have thousands and thousands of those, and we still have enough addresses. I like the way the IPv6 is set up. To me, it makes a lot more sense. It's cut and dried. The first 64 bits of that is the network address. The last 64 bits is the interface or the NIC address. And embedded in that will be your 48-bit MAC address of your network interface. The new layers and the new requirements and guidelines for the next version of the internet, everything is going to be traveling in encrypted format across the network links. Much more secure, much easier to control, in my opinion, and we will never, ever even come close to running out of available addresses. Okay? We're getting close to that in the IPv4 world right now. Okay? So that is your transmission control protocol, TCP/IP. Okay. Now, network communications in general, let's say, yeah, we're doing good on time frame here. Remember, guys, we're going to be cutting it off at 2:30 this afternoon. I have to go to the cardio appointment. So network communications in general, the transport layer I was telling you about, it decides based upon the type of application you're running, what communication port that it's going to be communicating with on the target systems. They're very standardized communication ports. Those are called common ports. And a couple of documents I gave you guys to download identify what these common ports are. There are a total, and these are all logical communication ports on every computer system. There's 65,535, it's actually 65,536 of those associated with every machine processor. They are very specific. The different software protocols communicate by default anyway over very particular communication ports. For instance, this video transmission we're doing here, that is a combination of two basic communication ports on your computer system that you're receiving the video in. And it's port 5060 and 5061, 5060, 5061. There, if I'm communicating with a web page, for instance, when you guys keyed into my website, if you went to it yesterday, my website is secure website, so it uses port 443, the HTTPS protocol. The unsecure websites, HTTP, utilizes port 80. You have email ports and protocols. There's three different email software protocols. There's post office protocol, they call it POP3, that communicates by default on port 110. You have IMAP, Internet Message Access Protocol, that communicates by default on port 143. And then you have the simple mail transport protocol, SMTP, that communicates by default on port 25. And then there's also secure ports that most of the protocols will utilize as well. Now, for you to prep for answering questions about ports and protocols on your exam, you need to memorize this chart right here. This is your well-known ports. The questions that they're going to ask you about these ports, they'll throw them at you in a couple of different flavors. They'll make reference, for instance, to the software protocol that you're using, FTP or DNS or server message block or remote desktop protocol, and they just assume that you know the port that it communicates over, or vice versa. They'll make reference in the question to the port and then just assume that you know the proper software protocol that operates over it. As part of your homework assignment tonight, I want you to make you some flashcards of these well-known ports, and I want you to look up what each of the protocols are. You got FTP, Server Shell, Telnet, Simple Mail Transport Protocol, Domain Name Services, Dynamic Host Configuration Protocol, Hypertext Transport Protocol. There's also Server Message Block, Hypertext Transport Protocol Secure, Remote Desktop Protocol. This is your directory services, Lightweight Directory Access Protocol, Internet Message Access Protocol, and there's Post Office Protocol. Look up all of those, read a little detail in your workbook about those, and know those communication ports and the protocols that operate over those. And that will assist you in answering the questions. And reading the detail, you'll see what they're used for. Okay. So Wireshark is also a tool that I can utilize to see and look at the communication ports and protocols, of the data frames, the data packets. Now, I mentioned to you also about the TCP as opposed to the UDP communications. TCP, Transmission Control Protocol, is interactive. When I start up a TCP session, my computer makes a connection to the target system I want to talk to, and it sends what's referred to as a sync flag, a synchronization request. So my computer sends a message that says, I'd like to talk to you on this port. If that port is indeed open and waiting for a communication session, it sends back two flags. It sends back the synchronization and the acknowledgement flag, a sync ACK. That tells me, yeah, that computer is ready to establish the session. If indeed, then I turn around and send back the handshake, as it were, the acknowledgement flag to them. Now we're talking together. We are bound. We have a session that's bound. And then in the TCP/IP world, it's timed, it's synchronized, guaranteed delivery. If I send a data frame and it's damaged or dropped off the network for whatever reason, maybe the router decided to take a different route and exceeded the number of available hops, so it dropped it off the network. That target system sends back to me. It says, I didn't receive sequence number 1535. Would you please resend that? And it'll keep doing that until it receives all the data. Then it resequences it and plays it back to whatever the target application happens to be. You see. So some of the protocols only operate in that, interactive time synchronized mode. Some of the protocols only operate in the UDP mode, the user datagram mode. And then some of them are selectable, how they do it either or, and they make that determination at communication time. So they decide if it's going to be, operating in the TCP or the UDP mode real time. And it bases on different metrics. Is the network path good? Is it bottlenecked? Am I exceeding hops between one location to another? So it evaluates those metrics real time prior to starting the communication session, and then makes it based on that. Okay. DHCP is your dynamic host configuration protocol. Really cool. It manages all of the IP addresses. Okay. And it follows this DORA, they call it, mechanism, and that is it's do, respond, do, orient, respond, optimization there going on that. The really cool thing about DHCP is there may be certain systems inside of my larger network that I always want to have the same IP address, a static IP address. I can either go to those machines, those systems, and manually configure all of that, or I can have DHCP do it for me dynamically. I give the MAC address of those systems that I want to always have the same IP address to the DHCP server. This function is called IP reservation, by the way. So it says, yep, my web server, I always want it to have the same IP address. Here's the MAC address. Here's the IP address I want you to assign to that. The DHCP server says, all right, every time that system comes online, it searches its table and says, for this MAC address, always assign this IP address. It also takes that IP address out of the available pool of IP addresses so that I don't make the mistake of assigning duplicate IP addresses to computer systems in the same network. You see. So I like that IP reservation. It keeps old dyslexic Donnie from going out there and manually configuring a whole bunch of things that you may not ever make sense of. Here is the DHCP thing in general. Told you guys earlier, system comes online. First thing it does is discovers where the DHCP server is. Okay. the DHCP server, and it sends my MAC address to them. DHCP server says, all right, here's the MAC address. Here is the IP address I am offering up to you for the duration of this session. Okay. And then I can either, yep, I'll take that, or I can say, no, I don't want that one. I want a different one. But the DHCP server then logs in its database. All right, for this MAC address, here's the IP address for this session. It also, remember I talked about the ARP cache, which is on my system. It updates my ARP cache and the ARP cache that's available to all the users in the network. It says, all right, here's the IP address that's assigned to this MAC address, and it will be that until this session expires. Okay. So it gives me all of that information. It's the blink of an eye kind of stuff. I mean, you don't really see that exchange because it happens so rapidly. I have a DHCP applet program that is built into my typically, the DHCP server is configured from a domain, Windows domain server level. So I can go in and configure it. I configure it and set up all the functions of the IP addresses, the pool of available IPs that I want to have. I can set that up like we are looking at earlier in my router gateway appliance and have it play the role of the DHCP server as well. Now, as far as the internet is concerned, I don't know if you guys remember when the internet first came online, way back in the dark ages of the internet, there were originally three what they call top level domains defined. There was .com, .net, and .org. Now, almost immediately after those came online, you started seeing other top level domains. For instance, top level domains for the countries all over the world. UK, RU for Russia, CA for Canada, and the list went on and on and on for all of the individual countries. And then now, I mean, there's so many top level domains, it's not even funny. You have a top level domain for everything. .sales, .mail, and the list goes on and on. And then down subordinate to those, we have what's called subdomains. Subdomains are typically further subdivisions of an organization. On my personal website, I have now currently 4 subdomains. I'm not using any of them as of yet, but I will be in the future. I'll have student.donniehelms.com. I'll have wiki.donniehelms.com. I'll have store.donniehelms.com. And I have recently changed this one. It's going to be podcast.donniehelms.com. I have several podcasts in the channel here, getting ready to launch those things later on as well. So that combination of the subdomain, the domain name, and the top level .com, .net, whatever it happens to be, that's referred to as a fully qualified domain name. Now, every computer system in a network also has an extension on that. And a good example is right down here at the bottom of this. pc.corp.515support.com. That's a fully qualified domain name for this particular PC. Okay. So down in that domain name system, it will track all of those resources. Inside of the DNS, there's about, I don't know, half a dozen or so different types of resource records there. They have host records. One of them's called an A record, which identifies an IPv4 host. There's a quad A4A record type that identifies IPv6 host machines. The version 6 addressability now is being utilized already, but only internal in autonomous networks. It's not supported as of yet over the public internet, they can't bring it on fast enough for me. But I've got a server SRV type text or record type in the DNS. I've got a TXT, which is just a documentation. I've got a reverse lookup record. It's called a pointer record, PTR. So if I happen to know the IP address of a domain, but don't know the domain name, I can do that reverse lookup on that. DNS also has baked into it a query language. I can run queries against the DNS server. And there's actually a Windows-based command called NSLOOKUP, which will allow me to make queries in the DNS server. And in the Linux world, there's a command called dig, which will allow me to do a bunch of different functions in DNS, querying being one of those. The information that I get back from those servers is based upon the type of resource record that I see inside those servers. It also houses things like the mail exchange MX record. There's this CNAME record here. That's a common name. It's sort of been replaced. They still use them, but it's been replaced by these two types of the A and the quad A record for IPv4 and IPv6 data. I also have a DNS manager application, management level application in the Windows environments as well. And all of your other operating systems have these management consoles that are available to basically manage set up and manage the DNS server. Okay. So, typically you have to have administrative privileges to use these things according to how the security is set up on a particular system. Also, inside the DNS server, I set up additional functionality for my email services. I will set up these records, and basically, I'm defining what people call their spam filter. I set up the sender policy framework, which includes these two downline type of record filters, I guess is the best way to put it. Any the digital signatures or key structures that are utilized for encrypted or secure email, I store those in the DKIM area, the domain keys identified mail. I set up my what they call the demarcation point, which houses my spam filter and decides who I can and cannot communicate with and under what conditions. So all of that is also defined inside of my DNS server as well. Now, I talked about the virtual local area network interface. That is well beyond the capability or the reach of this particular program. But in essence, what it allows me to do down at the switch interface level on these managed multi-layer switches, so I've got a 48 port switch. I can further isolate the computers that are physically plugged into the same piece of equipment in their own local area network. So I can set up VLAN 10, VLAN 20, VLAN 30 on the same switch. Let's say I assign the computers that are plugged into ports 1 through 8 to VLAN 10. The computers that are plugged into ports 10 through 23 are VLAN 20, and so on and so on. Well, those VLANs then further isolate those computers, and even though they are physically plugged into the same piece of equipment, they cannot communicate directly with one another. Their communications, a computer in VLAN 10 has to have its information routed through a router device to communicate with the users in VLAN 20. So it's an excellent way of further subdividing your network into like departments or divisions, but it also plays a role of cutting way down on the individual pieces of equipment you would otherwise require to separate those local area networks physically. So I'm just doing it virtually. Okay. Virtual private networks like that are really, really starting to be used a lot, and in coordinates with the VLANs as well. Now, VPN connection, virtual private network connection, is typically a client server kind of thing. You run some type of a VPN client on your workstation. And Kaylee, you were asking about this earlier. It is literally like drilling a tunnel through the internet. Okay, taking the tiniest little diamond-headed drill you could imagine and drilling a tunnel through the granite wall, which is the internet. So you got all that protection around the connection already. And then the VPN client allows you to wrap multiple layers of encapsulation and even encryption around that communication link too. Okay. Very secure. Nobody can tap into it. Okay. Unless they have your VPN credentials anyway. There's two flavors of setting up the VPN. There's one called a client to site, where you have a VPN client, your home user, whatever. communicating typically over the most unsecure network on the planet, which is the internet, through that VPN tunnel. And it utilizes protocols called tunneling protocols. That's the second layer of encapsulation. But it communicates directly with a VPN gateway device. And more often than not, now we see the VPN gateway and the router device, composited into a singular appliance. That's called client to site. We also have the setup here, it's called site to site VPN connectivity, where you have a VPN gateway like in a home office and a branch office, VPN gateway sitting at the network perimeter, and they go ahead and pre-establish multiple tunnels. So the users on the end, they don't have to establish a new session. They just put data down those very, very secure virtual private network client or virtual private network tunnels through the internet. So just about the most secure environment you could ever imagine. Okay. Going to be assigning this particular lab activity for you guys to do as homework tonight. So get ready for that when we kick it off here this afternoon. Okay. So that is your network configuration concepts in general. Okay. Now let's see, 120. Yep, still going good here. I want you guys to navigate real quickly down here to the 6.7 module quiz. Also 20 questions total there. Okay. Now, you folks that have been joining us on the YouTube and on the internet, I'm going to stop that broadcast now. Thank you very much for joining us. Contact the folks at CED Solutions, and good Lord willing and the creek don't rise, maybe we'll see you all in the class in the not too distant future. Hope so. Kathleen, you can hang with us here if you want to. We're going to be halting the class at 2:30 this afternoon, Kathleen, and you are welcome to hang with us until that time if you wish. And like I said, participate as much as you wish. I'm going to set you guys up a quick timer here. Only going to do 20 minutes on this timer. Now that should give you time to go through and do this quiz, post the scores, and even grab a quick latrine break if you need to. So you guys go ahead and jump in and go through that quiz. This guy right here, 6.7 module quiz. And once you do the quiz, post those scores. And we will pick right back up on our next module here in a quick 20 minutes. You guys have fun with that quiz now, and I'll see you back here shortly. And once again, you folks that are joining us on the internet, thank you so much for your participation here. And we're going to go ahead and stop the broadcast